In the last lecture, we looked at how life likely originated on Earth. In this lecture, we will look at the Archean eon and Earth's earliest life. Earth processes usually destroy fossils before they can become preserved. Soft parts are eaten or decompose. Hard parts can be dissolved by groundwater, broken during transport, or crushed by burial. Preservation is tenuous and is the exception rather than the rule. There is bias in the fossil record. What this means is that some organisms are preserved over others. There is habitat bias. For example, marine fossils are most often preserved over terrestrial fossils. Even in terrestrial environments, aquatic or near aquatic fossils are preserved over, say, mountainous environment fossils. Hard parts are preferred over soft parts. More durable hard parts are preserved over less durable hard parts. For example, teeth are preferred over fragile bones. Large fossils are more durable and more easily found than small fossils. And frankly, spectacular fossils are more likely to be collected than boring fossils. We have seen how geology dictates life. Now we will look at how life alters the planet. These are referred to as biogeochemical cycles. We looked at one when we looked at the carbon cycle. Even parts of the rock cycle are dependent on life. Biology affects the planet by altering the geosphere, hydrosphere, atmosphere, and climate. Life alters the geosphere through both biological weathering and the precipitation of minerals in shells to accumulate as sediment. Life alters the hydrosphere through metabolism by removing and adding different chemicals into the water. Life alters the atmosphere by producing and removing oxygen, carbon dioxide, and methane. And life's interactions with the planet, especially its atmosphere, can alter climate on both a short-term and long-term basis. For example, methane and carbon dioxide trap heat in the atmosphere. Archean Earth was very different. There was little to no oxygen in the atmosphere. There was much less life in the seas and no life at all on land. Intense meteorite and asteroid bombardments were ongoing, and we had a much hotter interior with more volcanism. Rocks older than 3.5 billion years are rare, but they do exist. The oldest minerals found to date are zircons that formed in the presence of water 4.4 billion years ago. The zircons were eroded out of older pre-existing rocks and incorporated into younger rocks. So these zircon grains provide evidence for both continents and water on Earth's surface as long as 4.4 billion years ago, just 200 million years after Earth formed. The oldest sedimentary rocks found are from West Greenland and have been dated at 3.85 billion years. The sediments were deposited in a shallow marine environment along a volcanic shoreline similar to Surtsey. Although warm, the climate was not inhospitable to life, but no oxygen was yet present. These sedimentary rocks are carbonate rocks, limestone, as well as iron-rich rocks. Carbon and iron stable isotopes from these rocks indicate complex and diverse biology was present. These are chemical fossils or biomarkers. Now, we do have fossil cells preserved in ancient rocks. The fossils were discovered in the chemical sedimentary rock called chert, which is microcrystalline quartz. Chert is very abundant in Archean rocks, and because it is so fine, it efficiently preserved ancient cells. This 3.465 billion year old fossil is from the apex chert in Australia. When it was first discovered, it was because the image was so blurry that some people thought it was really not a fossil at all. With new technology for imaging, it shows that the cell's internal structure and 3D shape confirm this as the earliest fossil cell found so far. It looks like a cyanobacterium. These long, thin fossils circled in blue are preserved in the Gunflint chert. The Gunflint Formation is a sequence of banded iron formation rocks that are exposed in the Gunflint Range of northern Minnesota and northwestern Ontario, along the north shore of Lake Superior. The black layers in the sequence contain microfossils that are 1.9 to 2.3 billion years in age. In northwest Australia, sedimentary rocks dating from 3.55 to 3 billion years can be found. These rocks are associated with shallow marine environments. They are unusual in that they have not been deformed nor metamorphosed, so they contain an excellent record of the time period. These rocks contain stromatolites, which are laminated mounds and domes constructed by microorganisms. They are trace fossils of the organisms that built them, so they are often referred to as Earth's earliest or oldest fossils. This photo shows what one of these laminated mounds looks like, though they can have many forms. This is another photo of these Australian stromatolites. These are cone-shaped laminated mounds. They were found with wave-affected sediments, so we know that they formed in very shallow water. And if we compare them with modern stromatolites, we can infer that these ancient trace fossils were formed by cyanobacteria. Today, stromatolites, such as these in this photo from Shark Bay, live in highly restricted environments that inhibit organisms that might otherwise eat the bacterial mats. Shark Bay is hypersaline, and the stromatolites are restricted to the intertidal zone. Stromatolites are the most conspicuous fossil for approximately 3 billion years, from 3.5 billion to 550 million years ago. They are not as common in the Archean as in the Proterozoic because Archean shallow marine environments were limited. There was also no ozone layer to protect them from UV radiation, which means they often lived in several meters of water depth for protection. The stromatolites were very complex communities of microorganisms living symbiotically. The earliest stromatolites are Archean and first appear in the fossil record between 3.4 and 3.5 billion years ago. At approximately 3.1 billion years, their morphology, which is their form, diversifies. Approximately 2.9 billion years ago, they expanded environmentally into soft, silty seafloors, followed by expansion to salt lakes on land 100 million years later. Stromatolites are sometimes referred to as bacterial mats or mounds, and even though they were abundant in the Archean, they were still geographically constrained until about 2.5 billion years ago. By 2.5 billion years ago, at the end of the Archean and beginning of the Proterozoic, Earth's interior had cooled somewhat. Crust had thickened and strengthened, and modern plate tectonics took root. Continents became larger, more stable. Continental shelves expanded, providing excellent habitat for stromatolites. Proterozoic stromatolites diversified and developed new and complex shapes indicative of a complex ecology. Stromatolites increased significantly with the onset of the Proterozoic. Cyanobacterial photosynthesis produced oxygen, which reacted with dissolved iron to form banded irons. However, atmospheric oxygen did not become significant enough to leave a geologic record until 2.3 billion years ago. The slow production of oxygen can be traced to initially few shallow marine habitats to support stromatolites and limited essential nutrients, especially phosphorus needed for life. Beginning in the Archean, about 3.8 billion years ago, and continuing until about 1.8 billion years ago in the Proterozoic, sedimentary rock made up of alternating layers, thin layers or bands of chert and iron oxide formed. The formation of these banded irons changed the color of the Precambrian seas from green to blue by the removal of large quantities of dissolved iron from the world's oceans. This photo shows a large block of banded iron. The red bands are oxidized iron. This is a photo of microscopic banding. The significance of the banded iron formations are their roles as oxygen sinks, reacting with oxygen produced during photosynthesis in aquatic environments, basically oceans and lakes. Not until all of the available reduced iron was exhausted could free oxygen begin to accumulate in the atmosphere. Reduced iron, or iron 2, is relatively soluble in water. Oxidized iron, or iron 3, is essentially rust and is insoluble. Chert would have been precipitated more or less continually, but iron would precipitate only when oxygen became available during an oxidation event. When oxygen was not available, iron would be replenished by submarine volcanism and by weathering and erosion of the continents. The Great Oxidation Event, the GOE, was a result of biogeochemical changes causing and caused by oxygen. The most precise estimate of the timing of the event is 2.316 billion years ago, plus or minus 7 million years. As a result, the surface chemistry of Earth's air, land, and water changed forever. The most important change for life was the development of the ozone layer, which shielded Earth's surface from lethal UV radiation. The GOE was likely the first biologically induced climate event. There was a slow and steady increase in oxygen throughout the Archean oceans, followed with a large, sudden increase in atmospheric oxygen between 2.4 and 2 billion years ago. The evidence for the large increase includes the absence of uraninite in rocks younger than 2.3 billion years. Uraninite is a uranium ore that oxidizes very easily in the presence of oxygen. The appearance of red beds also occurs at 2.3 billion years ago. Red beds get their name from the oxidized iron in the sedimentary rocks. It takes oxygen to form red beds. Atmospheric methane reacted with the atmospheric oxygen, thus removing this methane greenhouse gas. The removal of methane caused temperatures to drop, and an ice age ensued from 2.4 to 2.2 billion years ago. This is the end of part 1. In part 2, we will look at the evolution of the eukaryotes.